So working with ratio of areas, we're going to have two places to focus. First off, areas of triangle. Areas of two triangles. Ratio of their areas. What's that? It is. It's like a bulleted item, you know, that type of thing. Okay? Areas of two triangles, and there are three things we can look at with areas of two triangles. The ratio when they have the same base. And leave a little space in your notes. The ratio when they have the same height. And finally, the third item, the ratio of their areas when they are similar. Then our next focus is, in general, the ratio of two figures when they are similar. So our next bulleted item that we'll look at is the ratio of the areas of any two similar figures. Close. Because it's area and you're multiplying two corresponding side lengths, it's the square of that. So the areas of any two similar figures. Part of what we're going to look at when we're looking at these three items under the areas of two triangles is, what can this look like? When the triangles have the same base, what can this look like? So it might look like this type of thing. The triangles, here's one triangle, here is another triangle, and these two triangles actually have the same base length, but different heights. Another way this can look is, you have the two triangles that share this side, but are not one on top of the other. So they have the same base length here, but different heights. Okay, so that's what it can look like if you have areas of two triangles with different heights. The one can be completely inside the other. You could have a triangle like this, and then the other triangle going like that. Okay, so that's what it can look like. Here we have the two heights. This one's height is in green. This one's height, a height is always from a vertex perpendicular to the opposite side, is maybe a little shorter. Extend that side. That's the height of that triangle. So we have a height 1 and a height 2. You might say this is our height 2. We put a little subscript 2 and a height 1. That would be the same with each of these. We have the two heights represented by, and if this is a right triangle, then that actually is the height of that triangle. We have these two heights. But in every case, the base is the same. And again, extend this side a little bit, maybe that would be perpendicular. I'm too close to the board to really make a good judgment off of that angle close. Okay. In every case, what we have here is the area of the first triangle to the area of the second triangle is, since we find the area of a triangle by going 1/2 the base times the height, then we'll have 1/2 the base, which is the same in both triangles, times height 1 over 1/2 that same base times height 2. And you can see, since you know how to reduce fractions, the 1/2s will reduce and the base is reduced. So you just get the ratio of their heights. If the triangles have the same base, then the ratio of the areas is the ratio of the height. I'm going to shrink this stuff so I have room to write. When they have the same base, then the ratio of their areas is the ratio of their heights. So our next piece then is when they have the same height. And again, the first thing we're going to focus on, what does this look like if they have the same height? What it usually looks like when the two triangles have the same height is that they share an edge and their bases are on the same line, is what it usually looks like. So we have the green triangle and the blue triangle that share an edge, share a vertex, and their bases are on the same line. Yes, David? Okay, let me see if I can help you see that. Yeah. Okay. Now can you see it? You got it now? Okay. So now when the triangles have the same height, this is what it usually looks like. Two triangles actually share an edge with a common vertex that comes down to a length, or a line rather, where both of their bases lie. You can see then that the height of both of these triangles will be that distance right there. I think I'd like to make that be a different color. We'll try to hit that down arrow. Properties, green. Okay, that's the height of both triangles. Now the bases of both triangles, base 1 and base 2, are different. And again, if you look at the ratio of their areas, and I'll make this be black, ratio of area 1 to area 2, you're going to have, since the area of a triangle is 1/2 the base times the height, 1/2 base 1 times that common height, and the area of triangle 2 is 1/2 of base 2 times that common height. And again, since you know how to reduce fractions, the 1/2s reduce, the heights reduce, leaving you the ratio of the two bases. So if the two triangles have the same height, then the ratio of their areas is the ratio of the bases. And I think I'll do this. Base 1 to base 2. Okay, you're ready to move to the next one. When the two triangles are similar, then what happens is, in fact, the base to the height will be the same ratio. Base 1 to base 2 will be the same ratio as height 1 to height 2. If the two triangles are similar, then the ratio of any two corresponding parts will equal the scale factor. So that will equal our scale factor, which we'll call C. Which means when you look at the two areas, since your area of triangle 1 is going to be 1/2 of base 1 times the height 1, and since the area of triangle 2 is going to be 1/2 base 2 times the height 2, and since the 1/2s reduce, we just have base 1 to base 2 times height 1 to height 2, which is just equal to your scale factor, which we're calling C, times itself. So it's just equal to C times C, or the square of your scale factor. Okay, and the Branson, Nick, and bar tapping. C's are not grabbing into there. Now, what happens with similar triangles, as in the ratio is the square of the scale factor, happens with any two similar figures. And that is our last bulleted item. So we are going to now go to our theorem, which is our last bulleted item, and deals with any two similar figures. So areas of two similar figures. Is theorem 11.7.
What does that say?
This piece up here in blue, the ratio of their areas is the square of the scale factor, which is the ratio of any two corresponding sides squared. Theorem 11.7, if the scale factor of two similar figures is A to B, part 1, the ratio of the perimeters of those two figures will be the same as the scale factor, which is A to B. The ratio of their areas, part 2, will be the square of the scale factor. Which is A squared to B squared. Now, a little bit of the reason behind this. If you have two figures that are similar, does not matter what those figures look like. Because if you have, say your scale factor is a 1 to 2, that would be x, this would be 2x, y, 2y, because always your size will be 2 times if it's a 1 to 2 ratio. So let's just continue z, 2z, and w, 2w. Let's find the perimeter of these two figures. The perimeter of the first figure, can't even spell perimeter. So perimeter 1, okay, is going to be x plus y plus z plus w, or w plus x plus y plus z. Perimeter 2 is going to be 2w plus 2x plus 2y plus 2z. Which is just the same thing as 2 times w plus x plus y plus z. So we can see that the ratio of their perimeters will just be 1 to 2, like the rate their scale factor was. The perimeter of the second figure will be 2 times the perimeter of the first figure. No matter what your scale factor is then, the ratio of the perimeters will be the same as the ratio of two corresponding sides, which is your scale factor. Now, if we look at the second part, which is the ratio of areas, because you always have to multiply 2 dimensions to get the area, because area of a rectangle base times height, area of a circle pi times radius squared. Notice that means radius times radius, right? Area of a square side length times itself, side length squared. Area of a triangle one half base times height. Because you always have to multiply 2 dimensions, you're always going to have that scale factor in there twice. Example, area of a rectangle. We have the first rectangle and the second rectangle, which is similar to that rectangle. What we know is if this side is, let me do it this way. If this side is your height and this other side is your base, and this figure is similar, then I just take my scale factor times the height to get this new height. Scale factor times the base to get this new base. If their ratio is a 3 to 1 or whatever, then this new height is going to be 3 times the height of that one, if it has a scale factor of 3 to 1. And this new base is going to be 3 times the base of that one. So what happens when you find the area of these two? The area of this one, which is base times height, and the area of this one, which is 3b times 3h. Notice you have that scale factor in there twice because you're multiplying 2 dimensions. So my result is going to be 9 times base times height, or 9 times area 1. You then are able to fit 9 of these rectangles in this rectangle if I can fit 3 of those sides on this side and 3 of those bases on this base. You can see that there would be 9 of those rectangles in this rectangle. Okay? So, again, Theorem 11.7, and I could do it more general, but Theorem 11.7, if the scale factor of two figures is a to b, then the ratio of the perimeters will be a to b, which is your scale factor. The ratio of areas is the square of that scale factor, a squared to b squared. Okay. Now, application. And there's some kind of fun problems in the application. First off, I am looking at simple problems, page 458, bottom in the written exercise. They tell me that problem number 1, that the scale factor is 1 to 4. Their question, what's the ratio of perimeters? Yep. And what's the ratio of the areas? What do we do to find the ratio of the areas if we know the scale factor? You square them. So 1 squared to 4 squared, which is 1 to 16. Okay. So now let's go the other direction. We'll do one more problem that's easy. I'm taking a look at number 7. They give me the ratio of the areas. And what did they give me from a ratio of areas? Was it 9 to 64? So then we're given scale factor, which you guys have already figured out, is the square root of that. So it's 3 to 8. Is this problem number 7? Look at the bottom of that page. You see it there, number 7? Okay. And then the ratio of the perimeters is the same as the scale factor. Always the same as the scale factor. Okay, so that's the easy ones. Now, a little more fun in the applications, making it a little harder. All right? And what I'm doing is moving to number 19. Number 19, I have 3 triangles. Triangle 1, 2, and 3. I'll try to kind of draw it here. And they number them 1, 2, 3. And then they give me some side links. This is 9 and 9, 8 and 6. And they want to know, part A, ratio of triangle 1 to 2. Part B, ratio of triangle 1 to 3. And part C, nope. In 19B, use the fact, so on and so forth. Okay. So, first off, I have to look at triangles 1 and 2. I notice that they have sides right there that are in a line, and that they have a common side with a common vertex. What is the case about those 2 triangles? They share a side, which means that they have the same what? Is it base or height? They have the same height. Fact is, their height would be, if I'd extend this out, it'd be this perpendicular segment. That'd be the height of both of them. So the ratio of their areas is the ratio of their bases. So triangle 1 and 2 is going to be a ratio of 6 to 8, which reduces to 3 to 4. You want to take the order they give you. So if they go 1 to 2, that's what you want to have. Okay, now 1 to 3 is the question. When I look at this, thinking, okay, what are our areas and what are our ratios and what's happening here?
They share the base.
They have the same length of base. Do they also have the same height? I'm looking at now, let me pull this stuff off of there. I am looking at this triangle and this triangle. Why? Well, because if I can find how these two compare, then I can think, how does one compare to this whole triangle here? And that might help me know how one compares to this triangle over there. Why? What do we know about these two triangles, the one that is outlined in blue and the other half? They have the same area. Why do they have the same area? They do have the same base. They also have the same height, don't they? So they have the same area. Even if they're a different shape, they have the same base and same height, so they have the same area. Their height is, in fact, this perpendicular line that would represent, and I probably didn't draw it perpendicular, the distance from the vertex to this base that both of them have is 9. Okay? Now, what I know is triangle 1 to triangle 2 have a ratio of 6 to 8 or 3 to 4. Which means if this triangle has an area of 3, then this triangle has an area of 4, and the whole triangle, 1 plus 2, would have an area of 7, 3 plus 4. So the area of triangle 1 to this whole blue outlined triangle is 3 to 7. Let me say that again. These two triangles, 1 and 2, have a ratio of 3 to 4. So if triangle 1 has an area of 3, let's just suppose, and triangle 2 has area of 4, then the sum of them would be an area of 7, which means this one would also have an area of 7, because it's congruent. So then the ratio of triangle 1 to 3 is going to be a 3 to 7 ratio. Okay? Now, a few more kind of fun problems, and I'm going to stop recording here.